Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Here we will learn about different concepts related to civil engineering. Time to enter the world of civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about structural analysis, shear, and moment equations. In this video, we are going to learn about shear and moment equation for beams subjected to various loads. Representing shear and moment algebraically is very useful, as it allows the structural engineer to quickly identify critical stress areas in the beam. In most cases, it may not be possible to write down only one equation for shear or moment for the entire beam, rather it would be necessary to write multiple equations, one for each beam segment. This happens when the beam is subjected to one or more concentrated loads. For example, consider a beam, simply supported beam, having a concentrated load at point B. Since the load divides the beam in two segments, we need to write two equations for shear and two equations for bending moment. A pair equations for each segments. Let us take another example. Consider a beam, simply supported beam, having a concentrated load at point B and point C. Since the load divides the beam in three segments, here, we have three pairs of equations are needed for representing shear and moment, since the concentrated load divide the beam into three segments. For having multiple shear and moment equation, also arises, when the beam is partially subjected to distributed load. For example, here, the uniformly distributed load divides the beam into the segments. Segment AB, which is directly under load, and segment BC, which is load-free. Therefore, we need one set of shear and moment equation for the left segment of the beam and another set of equation for the right segment of the beam. Let us see another beam carrying uniformly varying load. See diagram. Here, the triangular load divides the beam in three segments, AB, BC, CD. Therefore, we need three pairs of shear and moment equation as a pair for each segment. Now, that we know it may be necessary to have multiple equations for representing shear and moment in beams. Now, let us talk about how we should go about actually formulating such equations. Given a beam, we always start by calculating its support reactions. So, Step 1, calculate the support reactions. Step 2, decide how many shear and moment equations we need. That is how many segments the beam is divided into two by the loads. Let us examine the several cases. Case 1, how many pairs of shear and moment equations do we need for this beam? See figure. Here, load divides the beam into the segments, therefore, we need two sets of equations. One set of equation for the left segment and another set of equations for the right segment. Case 2 here, the load does not divide the beam into multiple segments as it applied at the tip of the beam. As shown in the figure. Therefore, we only need one shear equation and one moment for the entire beam. Case 3 in the below figure. Here, the loads divide the beam into 3 segments. Therefore, 3 pairs of shear and moment equations are needed. From these cases, we can see that the required number of shear equations is always equal to the required number of moment equations, but this is not necessarily true. We could have loading patterns that makes the required number of moment equations more than that of the shear equation. Let us consider this beam, subjected to a concentrated moment at its midpoint. This causes sudden drop, a discontinuity in the beam internal bending moment at the point. Consequently, 2 equations are needed for representing moment in the beam. We need one equation for the left segment up to the point of discontinuity. We need another equation for representing moment past the point of discontinuity. However, the concentrated moment does not cause any abrupt change in shear. Therefore, we can represent shear in the beam using one equation only. Now, summarizes what we have so far. Calculate the beam support reactions. Determine the number of shear and moment equation, number of equations. This is done for formulating shear and moment equation. Now, let us talk about another step, where we cut the beam in each segment of the identified segment and draw the free body diagram. Cut the beam in each of the identified segment at some distance, say x, from the left end of the beam. For example, let us consider a beam as shown in the figure below. Here, in this beam we are going to cut it twice. One in segment AB and one in segment BC. Segment AB, segment BC. Note that the distance from the left end of the beam, the cut point, is labeled x, in both cases. Then we draw the free body diagram for each segment. Step 4. Formulate the equilibrium equation for each segment, and solve for the unknowns. Here the unknowns are the shear and moment at the cut point. Let us go through this concept using a simple example. Consider a simply supported beam subjected to a concentrated load of 10 kN, Kn. The load is applied 4 m from the left end of the beam. Formulating the shear and moment equations for the beam. Step 1. Find the support reactions. It involves drawing free body diagram and formulating the equations and solving them for the unknowns. Drawing the free body diagram. Formulating the equilibrium equation for the entire beam and then solving for the unknowns. Summation F x equals 0. Therefore A x equals 0. Summation F y equals 0. A y and b y minus 10 equals 0. Equation 1, summation m a equals 0. 10 times 8, minus 10b. Y equals 0 equation 2, on solving these equation we get A. Y equals 6 kN and B. Y equals 4 kN. Step 2. Determine the required member of shear and moment equation. Here, the load divides the beam into two segments. Therefore, we need two set of equation. We need a shear and moment equation for the left segment of the beam and another set of equation for the right segment of the beam. Step 3. Cut the beam in each segment, then draw the free body diagram of the left part of the beam. Here is the free body diagram when the beam is cut in segment AB. Here is the free body diagram. Here is the free body diagram when the beam is cut in segment BC. Step 4. Now formulating the equilibrium equation for each free body diagram. Then solving them for unknown shear and moment for the first free body diagram. For the first free body diagram, here, sum of the forces in the y direction equals summation F. Y equals 0, 6, minus V equals 0 equation 1, summation M. O equals 0, 6 times x, minus M equals 0 equation 2, from equation 1 V equals 6 kN, from equation 2 M equals 6 times x kN meter. Since these equations are written for the segment AB, they are valid only for x between 0 meter and 4 meter. For the second free body diagram, summation F. Y equals 0, 6, minus 10, minus V equals 0 equation 3. Summation M. O equals 0, 6 times x, minus x minus 4, minus M equals 0 equation 4. From these equilibrium equation 3 and equation 4 we get V equals minus 4 kN. M equals 40, minus x kN meter. This prior equation works only for x between 4 meter and 10 meter, where segment B is located. Summarizes the result. Shearing the beam is expressed algebraically using two equations. V x equals 6 kN, 0 equals x equals 4. V x equals minus 4 kN, 4 equals x equals 10. Equation 1 gives us the shear value in the beam when x between 0 meter and 4 meter. The second equation gives us the shear value when x is between 4 meter and 10 meter. Similarly, moment in the beam is expressed algebraically using two equations. The first equation gives us the moment value in the beam when x is between 0 meter and 4 meter. M x equals 6x kN meter. 0 equals x equals 4. The second equation gives us the moment value when x is between 4 meter and 10 meter. M x equals 40 minus 4x kN meter. 4 equals x equals 10. Moment at x equals 4 can be calculated using any of the above equation. Let us examine another example. Here half the beam is subjected to a distributed load and the other half is not subjected to any load. Writing the shear and moment equation for the beam. Step 1. Find the support reaction. Step 2. Determine the required number of shear and moment equations. Step 3. Cut the beam segment and draw free body diagram. Step 4. Write the equilibrium equation for each free body diagram and solve them for unknowns. Step 1. Find the support reaction. Summation F X equals 0. Therefore A X equals 0. Summation F Y equals 0. A Y plus C Y minus 500 equals 0. Equation 1. Summation M A equals 0. 100 times 5 times 2.5 minus 10C Y equals 0. Equation 2. From the above equilibrium equation we get A Y equals 375 Newton. C Y equals 125 Newton. Step 2. Determine the required number of shear and moment equations. Here, the load divides the beam into two segments AB and BC, therefore we need two sets of equations. A pair of shear and moment equation for segment AB and another pair of shear and moment equation for the segment BC. Step 3. Cut the beam segment and draw free body diagram. Free body diagram of the left part of the beam. Step 4. Write the equilibrium equation for each free body diagram and solve them for unknowns for the first free body diagram. Summation F Y equals 0. 375 minus 100x minus V equals 0. Equation 1. Summation M O equals 0. 375x minus 100xx/2 minus M equals 0. Equation 2. From equation 1 we get V equals 375 minus 100x Newton. From equation 2 we get M equals 375x minus 100x 2/2 Newton meter. Both the equations are valid for x between 0 and 5 meter. For the second free body diagram, summation F Y equals 0. 375 minus 100 times 5 minus V equals 0. Equation 3. Summation M O equals 0. 375x minus 100 times 5 x 5 halves minus M equals 0 equation 4. Solving the equation for M and V equals minus 125 Newton and M equals 1250 125 x Newton meter. In summary, shearing the beam is represented using these equations. V x equals 375 100 x Newton 0 equals x equals 5. V x equals minus 125 Newton 5 equals x equals 10. Equation 1 gives us the shear value in the beam when x between 0 meter and 5 meter. The second equation gives us the shear value when x is between 5 meter and 10 meter. Similarly, moment in the beam is expressed algebraically using two equations. The first equation gives us the moment value in the beam when x is between 0 meter and 5 meter. M x equals 375x minus 100x2/2 Newton meter 0 equals x equals 5. The second equation gives us the moment value when x is between 5 meter and 10 meter. M x equals 1251 x Newton meter 5 equals x equals 10. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.